In this video, I'll be walking through my notes on mechanical systems. A link to the PDF and a list of corrections is in the video description. Scalars and vectors. Vectors are quantities with size and direction. Scalars only have size. Here are a few examples. Scalars include pressure, temperature. For example, you can't be warm in a particular direction. Time, though this one is debatable at higher levels. Mass, you can't be massive in a direction. And energy does not have direction. Vectors, on the other hand, include displacement, where if you're displaced from A to B, that involves both a distance as well as a direction. You can have a velocity in a direction, an acceleration in a direction, we can apply a force in a direction, and we can also apply a torque in a direction, for example clockwise or counterclockwise. Distance versus displacement. Distance describes the length of the path an object has travelled. Displacement describes the difference between the object's start and finish points. Distance and displacement are only the same if the object has travelled along a straight path. So for example, an object moving along a straight path will have the same distance and displacement, whereas an object moving along a curved path might travel along this line here. However, its overall displacement is a lot shorter. Speed. Speed describes how quickly an object's position changes. The vector of speed is velocity. Its scientific units are meters per second, which we can write as meters divided by seconds, or if you accept that 1 over a second is second to the power of -1, we can also write ms minus 1. We can describe speed with the equation that our speed, symbolized by v, is distance divided by time. Note that our units of meters and seconds give us our final unit of meters per second. Using this equation in an example, how long does it take for a car moving at 10 meters per second to travel 25 meters? Using the equation, velocity is distance over time, which we can rearrange for t, substitute in our distance and velocity, which gives us 2.5 seconds. Acceleration. Acceleration describes how quickly an object's speed changes. Its scientific units are meters per second, which we can write as meters per second, or if you accept that we can write this as meters per second squared, and that 1 over second squared is second to the power of -2, we can also write this as ms minus 2. We describe acceleration with the equation acceleration is speed over time. When an object accelerates against its velocity, we say that it decelerates. For example, if we have a car traveling in a particular direction, if our acceleration was to act in the opposite direction, this would reduce the size of our velocity, and we would say that the car is decelerating. Using this equation in an example, a car accelerates from rest at 5 meters per second for 7 seconds. Calculate its new speed. Using the equation acceleration is velocity over time, rearranging it for velocity, and putting in our acceleration and our time, we get 35 meters per second. Equating vectors. Similar to scalars, vectors form equations. To do this, we can use these techniques. Circles are zeros, meaning that vectors forming closed paths equal 0. For example, if we had the vector a plus b plus c plus d, these all form a closed path, meaning that the path returns on itself, and so the sum of these vectors is 0. Similarly, we could write a plus b plus c, once again forming a closed path, and so once again the sum of these vectors is 0. This works no matter how many vectors you choose, so a plus b plus c plus d, once again all sum to 0. The second technique is equivalent paths, meaning that vectors or sets of vectors that start and finish in the same place are equal, so that a plus b starts and finishes in the same location as c, meaning that a plus b equals c. Similarly, a plus b gets you to the same place as c plus d, and so a plus b is equal to c plus d, and finally a plus b plus c gets you to the same place as d, and so a plus b plus c is equal to d. To be clear, this only works when we consider these as vectors with direction. Trigonometry refresher. In this course, you're going to be doing a lot of trigonometry. For this reason, it will be assumed that you know the basics of Pythagoras and SOHCAHTOA. For this reason, it's worthy of a recap. If we have a right-angled triangle, the longest side is what we call the hypotenuse, and if this is defined as our angle, then the side opposite is called our opposite side, and the side adjacent to it is our adjacent side. If we were to instead define this as our angle, then the opposite and the adjacent would be the other way around. Pythagoras tells us that the hypotenuse squared is equal to the opposite squared plus the adjacent squared, which we can rearrange for each side. The term SOHCAHTOA is a method of remembering trigonometric ratios. SO tells us that sine of the angle is equal to the opposite side divided by the hypotenuse. Ka tells us that the cosine of the angle is equal to the adjacent over the hypotenuse, and TOA tells us that tan of the angle is opposite over adjacent. Vector components. It is often useful to separate a vector into horizontal and vertical components. Knowing the total magnitude and the angle, we can use SOHCAHTOA. So if we have our vector here, pointing at a known angle, we can separate it into our horizontal and vertical components. If we note that this is our hypotenuse, this is our adjacent, and this is our opposite, for v horizontal, we can use that cosine of the angle is equal to our v horizontal divided by our hypotenuse v. Multiplying both sides by v gives us this equation here. We can do the same for our vertical using the SO relationship, which is that sine of the angle is equal to the opposite, our v vertical, divided by our hypotenuse v. Once again, multiplying both sides by v gives us this equation here. Momentum. Momentum is a measurement of motion that takes into account both mass and velocity. It has units of kilogram meters per second. As an equation, momentum symbolized by lowercase p is equal to mass times velocity. And so, as we can see, momentum takes into account mass and velocity in equal proportion. And although kilogram meters per second is quite a mouthful and might seem hard to remember, just bear in mind it's just the units of mass multiplied by the units of velocity. A bee and a car might travel at the same velocity, but have very different momentums due to their considerable mass difference. For example, a bumblebee and car traveling at 10 meters per second will, because of their very different masses, have very different momentums. Impulse. The longer a collision takes, the smaller the force. This concept is described by the following equation. Force is the change in momentum divided by the duration over which it changed. Impulse itself as a quantity is defined as the change in an object's momentum. So if you're asked to find the impulse, you're being asked to find the change in momentum. To understand this concept further, we can plot force and time on graphs. Consider driving in a car with a certain velocity. If you were to slam on the brakes, you will experience a large amount of force over a short duration. However, if you were to slowly brake, the force you'd experience would be smaller, but it would be spread over a longer duration. Because in both cases, we went from having the same amount of momentum to a momentum of 0, the momentum change is the same in both cases. Graphically, this change in momentum is represented by the area underneath this graph. Let's now use this in an example. A 0.050 kilogram tennis ball traveling at 6.2 meters per second rebounds off a wall and now travels at 5.9 meters per second in the opposite direction. The ball is in contact with the wall for 0.0045 seconds. Calculate the average force on the ball. We know the mass of the ball, we know the initial and final velocities, Important to note that because they are in the opposite direction, one of them needs to be positive and one of them needs to be negative. Which one doesn't matter. The only thing this will affect is whether your answer is positive or negative. I'll talk more on this after we've done the calculation. The last thing we know is the duration of the collision. To find the force, we need to use the equation of the change in momentum over time. We know the time, but we don't know the change in momentum. To find that, we need to take the final momentum and subtract the initial momentum. This is how you find the change in any quantity. Knowing that momentum is mass times velocity, we can make that substitution. Putting in our numbers gives us 0.61 kilogram meters per second. Now back to the question of making velocities negative. The way I set this question up was that our 5.9 was positive and our negative 6.2 was negative. The fact that we've got a positive change in momentum out means that it's pointing in our positive direction, which we've defined up here as this direction. So the direction of our change in momentum is the same. Now, if we had instead made this one positive and this one negative, our 6.2 would be positive down here, and our 5.9 would be negative, and if you pop that into your calculator, you'll still get 0.61, except it'll be negative. And because we have swapped the direction of positive and negative, the fact that our change in momentum is negative means it points in the negative direction, this direction here, exactly the same as before. Now, knowing our change in momentum and our duration, we can substitute these into our force equation, giving us 135 newtons. Conservation of momentum. The total momentum of a set of objects will only change if an external force acts upon them. This is called conservation of momentum. For example, if before we have an orange ball with a momentum of 20 towards the right and a green ball with a momentum of 30 towards the left, if we define this direction as our positive direction and add these momentums together, that gives us positive 20 plus negative 30, which gives us negative 10. If these two balls were to collide, we might see that afterwards, the orange ball has a momentum of 25 towards the left and the green ball a momentum of 15 towards the right. Once again, adding these momentums together, once again gives us negative 10. Our total momentum before and after is the same, and so momentum is conserved. Using this in a couple of examples, billiard balls experience gravity and the support force. Though they are external, they are also balanced. The net external force is therefore zero, and momentum is conserved. However, a ball in flight experiences an unbalanced external force due to gravity, and so consequently momentum is not conserved. And so to summarize, momentum can still be conserved if there is an external force, if that external force is balanced such that the net external force is zero, like it is here and like it isn't here. What is an external force? Consider a falling apple. As it falls, its momentum increases. We could say that momentum isn't conserved because gravity is an external force. An external force is a force applied by an object whose momentum we've ignored, often because it's impractical or impossible to measure. In the case of the apple, we've ignored the equal and opposite momentum the apple's gravity has imparted to the Earth. And so to summarize, even though it looks like our apple has gained momentum in such a way that momentum is not conserved, in reality, just as the Earth has attracted the apple has attracted the Earth. As a result, the Earth gains an equal and opposite upwards momentum, such that these momentums cancel out, and momentum is actually conserved. However, considering that momentum is mass times velocity, because the mass of the Earth is much larger than the apple, its resulting upwards velocity is much smaller. So small that it's impossible to measure, and it's easy just to call gravity an external force and say that momentum isn't conserved. Long story short, momentum appears to not be conserved only when a part of the system is ignored. I have here a neodymium magnet with a row of bearings attached to the left side. Introducing an identical bearing from the opposite side, the left end bearing is launched with considerably more momentum. How is momentum conserved in this case? As the bearing approaches, it experiences an attractive magnetic force, accelerating it and increasing its momentum. In return, however, the magnet and everything attached experience an equal and opposite attraction to the bearing, and an equal and opposite increase in momentum. We don't see this because of the friction with the table. However, if we repeat this experiment on a frictionless air table, we do. Thus, our initial momentum from the approaching bearing is equal to the momentum of the propelled bearing minus the momentum of the magnet and everything attached. So the initial and final momentums equal, and momentum is conserved. 2D momentum example. In the following example, we're going to determine the speed of ball B after the collision. And so we have billiard balls A and B and their respective masses. Before the collision, ball A has a velocity of 1.80 and ball B is stationary. After the collision, the balls move off at right angles, where we know the velocity of ball A as 1.10. The key idea we need to use is conservation of momentum. For that reason, we need to find the initial and final momentums. To determine the total initial momentum, the only thing with velocity is our ball A, and so we just need to find its momentum. Momentum is mass times velocity. We know both of these, which gives us 0.306 kilogram meters per second. Since we know the velocity of ball A afterwards, we can find its momentum afterwards using the same process as above, but with the final velocity, which gives us 0.187 kilogram meters per second. Now, to determine the final ball B momentum, we can draw a vector triangle. What this triangle is saying is that the momentum before, which is just this vector here, is equal to the final momentum, which is the ball A final momentum plus the ball B final momentum. And so this vector is this vector plus this vector. To find our ball B momentum, we can just use Pythagoras, where 0.306 is our hypotenuse, which gives us this equation here, that equals 0.242 kilogram meters per second. To determine the final ball B velocity, which is what we're ultimately trying to find, we just need to take that momentum and divide it by the mass. Doing so gives us 2.02 meters per second. Center of mass. Center of mass describes the average position of a set of objects weighted by their masses. Putting this more practically, two objects on a pivot will balance at their center of mass. So if we were to balance Earth and Jupiter on a pivot, because the mass of Jupiter is much larger than Earth's, the center of mass is therefore much closer. And now the step up from level 2 to level 3 is to describe this mathematically. Consider masses m1 and m2. If we were to specify some position as our x equals 0, then the distance to the center of mass from this location is going to be mass 1 times the distance from mass 1 to our x equals 0, plus our mass 2 multiplied by its distance, divided by the sum of the masses. Now, in many cases, we can simplify this by taking our x equals 0 and instead making it at one of our masses. Doing so makes our x1 0, and so this term disappears out of the equation. Our xcom is now the distance from mass 1 to the center of mass, and our x2 is the separation between the masses. And so to summarize, it's up to you wherever you make your x equals 0. However, in most questions, if you make it at one of your masses, it makes the problem much simpler. Let's now use this in an example. Consider the Earth and the Moon. The Earth has a mass of 5.97 times 10 to the 24 kilograms, the Moon has a mass of 7.35 times 10 to the 22 kilograms, and the distance between their centers is 3.84 times 10 to the 8 meters. Calculate the distance of the center of mass from Earth's center. And so we know the masses, and as I was mentioning on the previous page, because we're wanting the distance of the center of mass from Earth's center, to make the mathematics easier, we can make our x equals 0 at Earth, which means that our x1 is 0 and our x2 is the separation between them. So we can take our xcom equation, substitute in our numbers, which gives us 4.7 times 10 to the 6 meters. I have here a glass, 2 forks, and a matchstick. Balancing these just right, and spending an embarrassing amount of time doing it, we see what initially appears to be counterintuitive. All the weight is on the end of the matchstick, so why doesn't the matchstick topple? If we consider where the match is pivoting and draw a line through it, what we see is that we have a roughly equal amount of mass on either side of our line, meaning that our match fork structure has its center of mass above this pivot, and since their combined force of gravity acts from this point, it has a distance of 0. As the distance to our pivot is 0, no torque is produced. Center of mass in 2D. Finding the center of mass of objects in 2D is done by finding xcom and ycom. So if we have our two masses, plotting them in a coordinate system, we have our x distances, and we have our y distances. Our center of mass has the same, and so we just use our familiar center of mass equation, but for x and y separately. Let's use this in an example. Dave sits on a 2 meter by 3 meter raft of uniform density. His 12.3 kilogram fish box is in one corner and his 23.7 tackle box is in the opposite. Dave draws a coordinate system to figure out the center of mass between them. Calculate the coordinates of this position. And so representing the raft as a coordinate system, we can place our fish box at the origin, which, given the dimensions of the raft, puts our fish box at a x of 3 meters and a y of 2 meters. Knowing the x values and the masses, we can find our xcom. Putting in our numbers gives us 1.98 meters. Doing the same for our x values, putting our numbers in, gives us 1.32 meters, which we can plot on our coordinate system. Center of mass collisions. Provided there is no resultant external force, the motion of the center of mass will not change. And so if we have balls M1 and M2 colliding, provided there are no external forces, the motion of the center of mass throughout is not going to change. As the mention of external forces might suggest, this is really just a rewording of conservation of momentum. I have here footage of 4 separate collisions. Using Tracker, a video analysis program, I'll use each one to demonstrate a different collision-based concept. Collision 1, Symmetry. While the transfer of momentum in this collision may seem unintuitive, approaching this idea mathematically, imagining a puck moving right with a velocity of 10 towards a stationary identical puck, post-collision, the first stops, and the second moves right with a velocity of 10. For an observer moving at half the initial velocity, all the velocities are increased by 5 towards the left, causing each of the initial and final velocities to be equal and opposite, or in other words, symmetrical. If we consider the perspective of an observer moving at half the initial velocity, we see that the interaction is, in this frame of reference, symmetrical. Collision 2, Right angles. In an elastic collision, kinetic energy is conserved, meaning that the initial kinetic energy equals the sum of the final kinetic energies. If the masses are the same, we can divide out half m, giving the velocities in the form of the Pythagoras equation, an equation specifically for right-angled triangles, proving that there must always be a right angle between the final velocities of equal masses colliding elastically, as we observe here. Collision 3. Momentum conservation. Because there are no unbalanced external forces, we can assume that momentum is conserved, meaning that the difference between the initial and final momentums should be zero. Using the tracker data to calculate the difference, we get a difference of 0.76%, small enough to dismiss as random error. Collision 4. Center of mass. Another way of phrasing momentum conservation is to say that the velocity of the system's center of mass remains constant. Using tracker to plot this, we indeed observe the center of mass marked in green following a near constant trajectory. This is a melon with no momentum. Moments after the melon explodes, let's ask the question, what is the momentum now? If the melon exploded in space with no forces to impede it, we could add up the momentums of every single piece and find that they add to zero. However, in this case, we have two key influences. We have a force from our table, applied upwards to all pieces in contact with it, and we have the force of gravity, applied to every single piece. From the perspective of our melon, these two forces are external, therefore the melon's momentum is not conserved. Conservation of energy. Energy is never created or destroyed, only transferred into different forms. This idea is called conservation of energy and is one of the most important ideas in all of physics. For example, if we had 10 joules of electrical energy and we were to power a lamp, we might have 3 of those joules transformed into light and 7 joules into heat. The main takeaway is that this energy wasn't destroyed and these energies weren't created. This electrical energy was just transferred into different forms. For another example, we could have a ball with 35 joules of gravitational potential energy, and upon falling we could have 2 of those joules lost to air resistance and 33 transferred to kinetic energy. Finally, if we had a wood log with 100 joules of chemical energy, upon being burned, we might have 10 joules of that used as light and 90 joules as heat. Let's now go through an example. A tuatara falls 2 meters from a tree. Calculate its velocity just before it lands. The only information we're given is that we have a height of 2 meters. Now we can assume that the kinetic energy that the tuatara gains is equal to the gravitational potential energy it had before it fell. We know kinetic energy is half mv squared and gravitational potential is mgh. We can divide both sides by mass, effectively cancelling it out, giving us half v squared equals gh, getting rid of the half by multiplying both sides by 2, and then square rooting both sides, putting in our numbers, giving us 6.3 meters per second. Work. When energy has been used, we say that work has been performed. Work is essentially another term for energy, and so unsurprisingly, it has the same units of joules. When a force is performed over a distance, the work performed is given by force times distance. For example, if we were to apply a force to a mass on a spring over a particular distance. And now, just as an aside, let's apply that to an object falling from a particular height. In this case, the force is the gravitational force, which we know is given by mg, which means knowing that work is equal to force times distance, and knowing that the force is mg, and we can write the distance as the height, what we end up with is the equation for gravitational potential energy. Let's use this in an example. A 95 kilogram dirt bike is rolled up a ramp onto a 0.80 meter trailer. Calculate the work done against gravity. We know the mass is 95 kilograms, and we know the distance. We know that work is equal to force times distance, and although we have the distance, we don't have the force. However, we do know that the force is gravitational, so it must be equal to mass times gravity. Putting in those numbers, we get 930 newtons. Using that in our equation below gives us 740 joules. And now, just to be clear, it doesn't matter whether we lifted the dirt bike directly or took it up a longer path, the distance moved against gravity is the same in both cases, even if the total distance moved is not. Power. Power is the rate of energy consumption. It is measured in joules per second, which are commonly called watts, symbolized by capital W. As an equation, we can write that power is energy used over time. For example, a 25-watt stereo consumes 25 joules per second. Since our 25 joules divided by 1 second is equal to 25. Just the same, a 10-watt fan consumes 10 joules per second. Force. A force is an influence that acts to accelerate objects. It is measured in newtons, symbolized by a capital N. Isaac Newton came up with 3 laws that give an insight into the relationship between force and motion. Newton's first law states that an object will only change its motion, or in other words, its velocity, if a force acts upon it. For example, if we were to kick a ball, the ball goes from stationary to moving only because we've applied a force to it. The reason the ball eventually stops moving is because the force of friction acts upon it, changing its motion once again from moving to stationary. In summary, any time the velocity of the ball changes, it is due to a force acting upon it. Newton's second law states that when a force acts upon an object, it will accelerate proportional to its mass, so that when we apply a force to an object, that object is going to accelerate at a rate depending on its mass. For the same amount of force, an increase in mass is going to see a decrease in acceleration. Newton's third law says that forces exist in equal and opposite pairs. For example, if we had a brick on a table, the brick is going to apply a force downwards to the table, and in response, the table is going to exert an equal and opposite force onto the brick. We also see this with gravity, where the Earth applies a force onto the Moon, and the Moon applies an equal and opposite force onto the Earth. Circular motion. Objects in circular motion are described using the following terms. The radius is half the circle width. The diameter is the circle width, which is twice the radius. The circumference is the length of one lap, where a revolution is a complete lap. The term period, symbolized by capital T, is the amount of seconds per revolution, so the amount of seconds for our object to go around once. On the other hand, our frequency is the revolutions per second. As this language suggests, these two are what we call mathematical reciprocals, meaning that frequency is 1 over period, and period is 1 over frequency. We can furthermore write the velocity of our object as distance over time, specifically the distance of one lap divided by the time taken to complete one lap. Centripetal acceleration. As an object changes direction, its velocity changes, even if the size of the velocity does not. This is called centripetal acceleration. A force or combination of forces providing centripetal acceleration are called centripetal forces. Centripetal literally means center-seeking, which tells us that the centripetal acceleration always points towards the center, whereas the velocity points tangential, which is 90 degrees to this acceleration. Now, it's important to note that the centripetal force is not a force on its own, it is a role that other forces provide. So if I were to ask you what are the forces acting on the Earth as it goes around the Sun, the answer is only gravity, which provides the centripetal force. If you were to swing a ball around on a rope, the centripetal force is provided by the tension, and if you had a car going around a flat circular track, the centripetal force is being provided by the friction between the tires and the track. So in summary, the centripetal force is not a force itself, it is a role that other forces play. We can write the centripetal force mathematically as the mass times the centripetal acceleration. This is also equal to mv squared over r. And so if you wanted to find the centripetal acceleration, you could take this equation here and divide both sides by mass and find that the centripetal acceleration is just v squared over r. Let's now go through an example. A 1500 kilogram car drives in a circle of 20 meter radius on flat ground. It completes a lap every 60 seconds. Calculate the minimum friction force the tires must provide. Our mass is 1500 kilograms, our radius is 20, and our period is 60 seconds. To find our friction force is playing the role of our centripetal force, so we can describe it with our centripetal force equation, where we have the mass and the radius, but we don't have the velocity, so we need to find it. To do this, we can take distance over time, or in other words, circumference over period. Circumference is 2 pi r, and period is t. Putting in our numbers gives us 2.1 meters per second. Using this in our equation below gives us 330 newtons. I have here a container of water, coloured green and set to spin on a turntable. As it does, we observe the water moving outwards from the centre. To explain this, consider a particle of water within the container. As the container rotates, the velocity of the particle is tangential to the circle, and if no forces were to act upon it, it would continue in this direction. However, because the particle instead encounters the wall of the container applies a force to it, leaving it nowhere to go but up. The force the container applies to the water is acting as the centripetal force, where centripetal means centre seeking, because this force always points towards the centre. From the perspective of an observer rotating with the container, such that the container appears stationary, it would instead seem as though there is a force pushing the water apart. While this force does not strictly exist, and is more of a trick of perspective, it can still be a useful description in some circumstances. We call this fictitious force the centrifugal force. Banked corner. In this application, we have a car travelling around a banked corner at an angle theta. The centripetal force is provided by the unbalanced horizontal force. In this case, it is the horizontal component of the reaction force Fr sine theta. So if we do a vector diagram of our car, we have our gravitational force downwards. The reaction force is perpendicular to the surface, which is banked at our angle theta. And now because the car is not accelerating upwards or downwards, we know that the vertical forces must equal, which is to say our gravitational force must be equal to the vertical component of our reaction force, which is Fr cosine theta. Cosine, because if we make this our right angled triangle, this is our adjacent side, this is our opposite, and Fr is our hypotenuse. Using our car relationship, we know that cosine of our angle is our adjacent, which is our vertical, divided by our hypotenuse, which is Fr. Multiply both sides by Fr, and you get that the vertical component is Fr cosine theta. This leaves Fr with an unbalanced horizontal component, which provides our centripetal force. Let's now use this in an example. A 1500 kilogram car drives around an icy or frictionless 80 meter radius corner banked at 25.4 degrees. Calculate the speed the car must reach to successfully navigate the corner. We know the mass, we know the radius of the curve, and we know the angle of banking. We know our gravitational force is downwards, and we know that the support force, which is another word for reaction force, is at our angle of 25.4 to the vertical. Adding these two vectors together, we get an unbalanced horizontal component, which is our centripetal force. And now, knowing that this is our hypotenuse, this is our adjacent, and this is our opposite, because we can easily find the gravitational force using our mass, we might as well use the adjacent, and to calculate the speed, we need to figure out the centripetal force, so we need to know our opposite. This means that we need to use the TOA in our SOHCAHTOA relationship, which means that tan of our angle is our opposite, which is our centripetal force, divided by our adjacent, which is our gravitational force. Multiplying both sides by Fg and swapping them around, we just need to put in our numbers, where our gravitational force is just mass times the acceleration due to gravity, giving us 6,310 newtons. Now we know that centripetal force is mv squared over r. Solving this for our speed, we can multiply both sides by r and divide both sides by m, as well as swapping them around. Then take the square root of both sides, putting in our numbers, gives us 18.3 meters per second. Newton's law of gravity. All objects with mass attract each other. Two masses m1 and m2, a distance r apart, will attract each other with a force given by big G, which is the universal gravitational constant, equal to 6.67 times 10 to the negative 11 Newton meter square per kg square, times the product of our masses, divided by their separation squared. It's important to note that the force experienced by either is the same, even if one of the masses is much greater than the other. Let's use this in an example. Once again, we have the Earth and the Moon. We know the mass of the Earth, we know the mass of the Moon, and we know the distance between their centers. Calculate the gravitational force between them. Knowing the masses and the separation, and knowing our gravitational equation, we just need to put in our numbers, which gives us 7.62 times 10 to the 28 newtons. Orbital motion. Orbital motion is circular motion, where the centripetal force is provided by the gravitational force. So if we have two masses, for example the Earth and the Moon again, where the Moon is going around the Earth due to its centripetal force at a particular radius. Because we know that the centripetal force is provided by the gravitational force, we know that these must equal. We also have equations for each, where we can solve this for velocity by first cancelling out our mass. Important to note that the mass we're cancelling out is the mass of the object in centripetal motion, because when we make this centripetal motion equation, we're specifically interested in the centripetal motion of the Moon. We can also multiply both sides by our radius to cancel out the radius here and cancel out the power here. That gives us v squared equals gm over r, square rooting both sides, and we get a final equation. This equation you're not given in the exam. This is something you'll either need to remember or remember how to figure out. Let's use this in an example. Yet again we have our Earth and our Moon in centripetal motion. We know the mass of the Earth, we know the Moon's orbital radius, so let's calculate the Moon's orbital velocity. Knowing the mass and the radius, knowing the centripetal force is provided by the gravitational force, we can substitute the equations for each, divide both sides by m1, which cancels out m1, multiply both sides by r, which gets rid of the r over here, and the power of the r over here. That gives us v squared equals gm2 over r, square rooting both sides, putting our numbers in, gives us 1020 meters per second. Vertical circular motion. A bucket is swung in a vertical circle at the minimum velocity required. The centripetal force is provided by the tension and/or gravity force at different times. With the gravitational force downwards, that stays the same throughout. At the bucket's minimum velocity, at the top of the motion, the tension force is able to be zero, and the centripetal force is only provided by gravity. If you were to increase the velocity, then we'd start to get a non-zero tension force. If you were to reduce the velocity, the bucket would no longer swing in a circle. At the bottom of our motion, our tension force needs to do two jobs. It needs to not only provide the centripetal force, it also needs to oppose the gravitational force, since the gravitational force is now in opposition to the centripetal force, instead of providing it like it was at the top. This means that our tension force needs to be equal to our centripetal force plus our gravitational force. Subtract Fg from both sides, and you get this equation for centripetal force. When the bucket is descending or ascending, Fg is perpendicular to the centripetal force, and so has no effect upon it, meaning that the only force providing the centripetal force is the tension force. Throughout this motion, if we were to plot the energies, our gravitational potential energy is at a minimum at the bottom, since it's at its lowest height, and at a maximum at the top. Our kinetic energy, however, is the greatest at the bottom, since the bucket is travelling its fastest, and the least at the top, since the bucket is travelling its slowest. Measuring angle. Angle can be measured in either degrees or radians. 1 radian is equal to 57.3 degrees. We may also express an angle as a multiple of pi, where 2 pi is 1 revolution, or in other words, 360 degrees. So a full revolution is 2 pi, half a revolution, or 180 degrees, is going to be just pi. Half of that gets you a quarter of a revolution, and half of that, which is pi over 4, gets you an eighth of a revolution. Translational versus rotational. Pure translational motion occurs when the force points through the center of mass. So if we have a feather with a center of mass, if we apply a force that points through that center of mass, we're going to get pure translational motion, which is to say the feather will be moving, but it won't be rotating. Pure rotational motion occurs when the net force is 0, but the net torque is not. So if we had our feather and we applied equal and opposite forces, because the forces are equal and opposite, the net force is 0, however the net torque is not. So the feather is going to rotate, but it isn't going to change position. In any other case, a mix of translational and rotational motion will occur. Rotational motion. By now, we're used to the translational motion terms of distance, velocity, and acceleration. Rotational motion has the same, but in a rotational context. So instead of displacement, we have angular displacement, symbolized by theta, and is what we've otherwise just referred to as an angle. More specifically, it is a change in angle, and we measure it in radians. Instead of velocity, we have angular velocity, which is symbolized by omega. Specifically lowercase omega, as opposed to the uppercase omega that we use as a symbol for ohms. Angular velocity is the rate of angle change, measured in radians per second. We can write an equation, which is equivalent to velocity is distance over time, except with our rotational values. Instead of acceleration, we have angular acceleration, symbolized by alpha. Angular acceleration is the rate of angular velocity change, measured in radians per second, or radians per second squared. Knowing that the acceleration is change in velocity over time, we can write the same but with our rotational values. Linear to rotational. In this section, we're going to explore how we can relate linear and rotational quantities. Let's imagine an object traveling in a circle. And let's say, for example, it has traveled from this position here to its current position, giving it a linear displacement d. We can say the object is traveling at a constant velocity, and its acceleration points towards the center because it's undergoing centripetal motion. The circle it's traveling in has a radius r. The angular displacement theta can be related to the linear displacement with the equation d equals r theta. Similarly, we can relate our angular velocity with our linear velocity with the equation v equals r omega. And lastly, we can relate our angular acceleration with our linear acceleration with the equation a equals r alpha. Equations of rotation. As with translational motion, we can use kinematic equations to describe rotational motion with constant angular acceleration. For this, we can define the quantities initial angular velocity, omega I, final angular velocity, omega f, our time, angular displacement theta, and angular acceleration alpha. Our rotational kinematic equations are exactly the same as the linear ones, just with rotational quantities. Let's use one in an example. A lawnmower blade angularly accelerates from rest at 90 radians per second. The blade reaches a final angular velocity of 300 radians per second. Calculate the amount of rotations the blade makes as it speeds up. And so we have our angular acceleration, we have our initial angular velocity, we have our final angular velocity, and we're wanting to find the amount of rotations, for which we're going to need to find the angular displacement. The thing we don't have and don't care to find is our time, so we're going to choose the one kinematic equation that doesn't have time, which is this one here. Because our initial angular velocity is 0, since it starts at rest, we can cancel out this term. And now to solve for our angular displacement, we just need to divide both sides by 2 alpha. Putting our numbers in gives us 500 radians. To find the amount of rotations, we just need to take our angular displacement and divide it by the amount of radians in one revolution, which is 2 pi. Substituting in our 500 gives us 785 rotations. Torque. A force is an influence that acts to accelerate an object. A torque is an influence that acts to angularly accelerate an object. It has units of Newton meters. As you would have learned in NCEA level 2, if we apply a force at a particular distance, the amount of torque we're going to generate is equal to the force multiplied by the distance. Now at NCEA level 3, we need to understand how torque affects motion. Recall that a force on a mass causes acceleration, described by F equals ma. Similarly, a torque on a rotational inertia causes rotational acceleration, described by torque is rotational inertia times angular acceleration. Where rotational inertia is a new quantity, which we will be exploring in greater depth. However, for now, to put it in a little bit more context, what we've until now been referring to as mass is in fact linear inertia. And so whereas you can think of mass as the resistance to linear acceleration, rotational inertia is the resistance to angular acceleration. Let's use this in an example. A merry-go-round with a 2 meter radius has a rotational inertia of 500 kg/meter square. A child pushes the edge with a force of 150 newtons. Calculate the angular acceleration. We know that torque is equal to I alpha, and we also know that torque is equal to force times distance. Taking this equation here and solving it for angular acceleration by dividing both sides by I, putting our numbers in, gives us 0.6 radians per second. I have here a section of dowel fixed to a disc, attached to a rotary sensor. For this experiment, I'll be shooting the dowel in 2 different positions with a low-powered air rifle. In the first position, the velocity of the slug is roughly perpendicular to the dowel's radius. In the second position, this angle is less. Comparing the two, we see the perpendicular shot disc rotating at a much higher angular velocity, having experienced a much higher angular acceleration. This happens because the torque applied to the disc is equal to the radius multiplied by the component of force perpendicular to the radius. The radius is kept constant, and while we can assume the force is approximately the same in each case, in the first position, all of the force is roughly perpendicular, while in the second position, the perpendicular component is smaller, resulting in a smaller torque, smaller angular acceleration, and smaller angular velocity. The component of force that doesn't act to produce a torque and therefore an angular acceleration, instead acts to produce linear acceleration, which we see a hint of in the more pronounced wobble of the disc. Repeating the experiment on a smart cart, we can observe and measure the difference more clearly. Rotational inertia. Mass is resistance to acceleration. Rotational inertia is resistance to angular acceleration. Rotational inertia has units of kilogram/meter square. The rotational inertia of an object depends on its mass and how that mass is distributed. What I'll do now is go through 6 basic examples, and now although you won't find these equations on your formula sheet, if a question in the exam requires it, the equation will be provided. For a thin ring with a radius r, meaning that all the mass is concentrated at one radius, the rotational inertia is mr squared. This assumption that the mass is all at one radius, instead of being spread across a range, is only an approximation and is impossible in the real world. More realistic is a ring with a certain thickness, with an inner and outer radius. In this case, the rotational inertia is half m r1 squared plus r2 squared. A solid sphere of radius r will have a rotational inertia of 2/5 mr squared. Similar to our thin ring, we can imagine a hollow sphere where all the mass is concentrated at a fixed radius. In this similarly unrealistic case, the rotational inertia is 2/3 mr squared. For a solid cylinder of radius r, our rotational inertia is half mr squared. And finally, if we were to rotate a thin rod about its long axis, its rotational inertia is equal to 1/12 mr squared. I have here a rotating platform, 2 masses which can be moved to change the platform's rotational inertia, and a mass and pulley system which are used to apply a constant torque. For this experiment, we'll investigate how the position of the masses affects the angular acceleration. Initially positioning the masses 10 centimeters from the center, after 30 seconds, the platform rotates with a period of 0.53 seconds. To calculate angular acceleration, we divide the change in angular velocity by the duration over which it changed, where angular velocity is 2 pi over the period. Putting in these numbers gives us 0.40 radians per second to 2 significant figures. Repeating the experiment with the masses at double the original distance, after 42 seconds, the platform rotates with a period of 1.5 seconds. Putting these numbers into our angular acceleration equation gives us 0.10 radians per second to 2 significant figures, 4 times less than the last. To explain this, recall that torque is rotational inertia times angular acceleration, and that rotational inertia is always some constant times mr squared. Keeping the mass and torque the same, a 2 times increase of the radius will result in a 2 squared or 4 times reduction in angular acceleration. Rotational kinetic energy. The kinetic energy of a rotating object is described by Ek rot, the rotational kinetic energy, is equal to half the rotational inertia multiplied by the angular velocity squared. This is a 1-to-1 analog of our linear equation, Ek equals half mv squared. The total kinetic energy of an object is the sum of its linear and rotational kinetic energies. For example, a ball rolls down a ramp. At the top of the ramp, the ball has gravitational potential energy Eg. At the bottom, this is converted to linear and rotational kinetic energy. And so our gravitational potential energy is converted to our total kinetic energy, which is the sum of our linear and rotational kinetic energies. Angular momentum. Linear momentum describes the amount of linear motion an object has, taking into account its mass, aka linear inertia. This is described by the familiar equation, momentum is mass times velocity. Angular momentum does this in a rotational context. And so our angular momentum, symbolized by capital L, is our rotational inertia multiplied by our angular velocity. We can relate angular momentum and linear momentum with each other, considering the scenario with a mass with a particular velocity, traveling in a circle of particular radius. Its angular momentum is given by mvr. Or if you wanted to substitute in for linear momentum, we could write this as pr. Let's now use this in an example. An astronaut floating in space catches a 0.060 kilogram tennis ball moving at 15.5 meters per second. The ball strikes the astronaut's hand 0.820 meters from her center of mass. The astronaut's rotational inertia is 12.0 kilogram meter square. Calculate the astronaut's angular velocity. We have the mass, we have the velocity, we have the rotational inertia, and we have the radius. Knowing that angular momentum is I omega and is also mvr, we can take this equation here and solve it for our angular velocity by dividing both sides by I. Putting in our numbers gives us 0.636 radians per second. I have here a bike wheel and a length of string. Suspending the wheel from the string and then letting it go, we see the wheel flop down much as you'd expect. Repeating this again but giving the wheel a spin, the wheel remains more or less upright, though due to friction it eventually slows and topples. So why does the wheel stay up while it's spinning? When the wheel spins, it has angular momentum. The larger the angular momentum, the more resistant our angular motion is to change. And because angular momentum is a vector, change not only means the magnitude of the angular momentum, but also the direction. Angular momentum conservation. As with linear momentum, angular momentum is always conserved, provided there are no external torques. Consider a main sequence star collapsing to form a neutron star. Our main sequence star could have a typical rotation of once every 30 days. Because our star has a large radius, it has a large rotational inertia, and currently a small angular velocity. Upon collapsing to a neutron star, because the radius has decreased drastically, our rotational inertia has also decreased, and because angular momentum is conserved, assuming there have been no external torques, our angular velocity must increase. Neutron stars have been found rotating as fast as 700 times per second. Let's now use this in an example. A satellite rotating once every 15 minutes deploys solar panels, changing its rotational inertia from 1.5 times 10 to the 3 kilogram meter square to 6.0 times 10 to the 4. Calculate the new rotational period. And so we're given the initial period of 15 minutes, multiply that by 60, and we get 900 seconds. To find our initial angular frequency, we can use the equation 2 pi f. We don't have the frequency, but we do have the period, and we know that frequency is 1 over period, which allows us to write 2 pi over t. Putting in our 900 gives us 0.00698 radians per second. The question also gives us the initial and final rotational inertias. To find our new rotational period, we can assume that there are no external torques, which allows us to write that the initial angular momentum is equal to the final angular momentum. We know that L is equal to I omega. To find our final period, we need to find our final angular velocity, for which we can solve this equation by dividing both sides by I final. Putting our numbers in gives us 0.000175 radians per second. And now, as mentioned earlier, we know that we can write angular velocity as 2 pi over the period. Solving that for t final gives us 2 pi over omega final. Putting our numbers in gives me 35,900 seconds, or 598 minutes. Here we see a world record figure skater. As she draws her arms in, she reduces her radius, which reduces her rotational inertia. Because angular momentum is conserved and our rotational inertia decreases, her angular velocity must increase.
Once they're in their spin, the rotational speed is dictated by how tightly they can pull their mass of their arms and their free leg to their axis of rotation.
Simple harmonic motion. By definition, a system in simple harmonic motion will have an acceleration towards equilibrium and will accelerate proportional to its displacement. So if we imagine a pendulum at two different positions with an equilibrium here, the acceleration is always going to be towards equilibrium, and the larger its displacement, the larger the acceleration. Being asked to state these two conditions is extremely common in the exam. The motion of a system in simple harmonic motion can be described as sinusoidal, where the amplitude is the maximum displacement, and so this might represent a pendulum starting at equilibrium, swinging to its maximum displacement, swinging back towards equilibrium, through equilibrium to the other side to its opposite max displacement, and then back to equilibrium, and so on. The simple pendulum. For a simple pendulum, suspended at a length L, oscillating at a maximum angle theta, more on that later, the period of its oscillations can be described as 2 pi times the square root of the length divided by the gravitational acceleration. However, this equation assumes the small angle approximation. This requires that the angle must be small. The reason for this is that the equation specifically assumes that sine of the angle is approximately the angle. This is only reasonable when the angle is small. Representing this on a graph so you can see this better, a plot of theta against theta is just going to be a straight line, whereas a plot of sine theta against theta is going to give our familiar curve. As you can see for small angles, these two are roughly equal, but get less and less equal as the angle increases. To the point where at around 10 degrees, the error exceeds 1% and starts to affect values expressed to 3 significant figures, which is standard at NCEA level 3. And so the question as to how large can the angle be until it starts to affect our results, at this level, that answer is around 10 degrees. It is useful to separate the forces acting on a pendulum into tangential and radial components, where if we have our pendulum suspended, our radial component is in the direction of the radius, and our tangential is at a tangent. The forces acting are the gravitational force downwards, and the tension force which acts along the radial. If we imagine our pendulum at a certain angle, we can separate Fg into its tangential and radial components. If we have this angle here, then using SOHCAHTOA, this side becomes negative Fg cosine theta, and this side becomes Fg sine theta. The reason this one is negative is because we have defined this as our positive radial direction, and this is pointing in the opposite. For our tangential, this is the positive direction, which our component is pointing in, and so it is positive Fg sine theta. Breaking down our tangential forces, the only tangential force is Fg sine theta. This is because Ft is purely in the radial direction. This component accelerates the bob towards equilibrium. Breaking down our radial forces, the radial forces are Ft, since the entirety of it is pointing as mentioned in the radial direction, and our radial component of the gravitational force, which is negative Fg cosine theta. The net radial force provides the centripetal force, that is that Fc is equal to Ft minus Fg cosine theta. I have here a mass on a rigid pendulum with a force meter displaying the tension, setting it swinging, and creating a composite image. We see the tension is greatest at equilibrium and lowest at its maximum amplitude. This happens because the tension not only balances the downwards gravitational force of the mass, it must also provide the centripetal force to keep it in circular motion. Centripetal force is proportional to velocity squared, therefore since the velocity of the pendulum is greatest at equilibrium, so too is the centripetal force, and so too is the tension force that provides it. I have here a simple pendulum. As you may know, the period of a pendulum is only dependent on the length, which we can change, and the acceleration due to gravity, which we typically can't. What it doesn't depend on is the mass. Keeping that in mind, let's see what happens when we add mass. As you can see, each mass we add decreases the period every time. This happens because the way in which we're adding mass is moving up the center of mass. Since we take the length of a pendulum from the pivot to the center of mass, when we add mass in this way, we're effectively reducing the length and therefore reducing the period. pendulum at half height. What is the velocity of a pendulum at half its maximum height? So we'll imagine a pendulum at equilibrium and at its maximum amplitude and at its half height. The total energy at its maximum height is purely gravitational, given by mgh. The total energy at half its maximum height is going to be half of this gravitational potential energy plus its kinetic energy, dictated by whatever its velocity will be. And the total energy at equilibrium is just its kinetic energy, since at this point we've assumed that all the gravitational potential energy has been converted. Assuming conservation of energy, we can say the energy at the maximum height is equal to the energy at half the maximum height, where we've just defined the equations for each. What I'm now going to do is solve this for v half squared for the purpose of making a substitution into the next column of working. So we can divide out the mass. We can also multiply everything by 2, which cancels out these halves and leaves us with 2gh. We can then subtract gh from both sides. 2gh minus gh is just gh. And now, using conservation of energy once again, we can write that the energy at the maximum height is equal to the energy at equilibrium, where once again we defined the equations for each, dividing out our mass, and now knowing that gh is equal to v half squared, we can make that substitution, square rooting both sides, separating out our half and v equilibrium squared. We can write that v half is the square root of a half multiplied by the velocity at equilibrium, where the square root of a half is 0.707. And so while you might have expected that the velocity at half the height would be half the velocity at equilibrium, what we instead see is that the velocity at half maximum height is greater than half the velocity at equilibrium. Now I know that all of this working might have been a bit much, but the key takeaway is this statement here. Mass on a spring. A mass on a spring displaced from equilibrium will oscillate with a period described by 2 pi times the square root of mass over k. Furthermore, if we have springs in series, meaning that they're arranged like so, their combined spring constant is given by 1 over k total is equal to the sum of the 1/overs. For springs in parallel, however, arranged like so, the combined spring constant is just the sum of the spring constants. I have here 2 springs and a mass of 403 grams. We can determine the spring constant of each spring by measuring their periods, rearranging this equation for k, and substituting those values, giving us 21.6 and 19.3 newtons per meter. When arranged in parallel, spring constants add together, which predicts a period of 0.62 seconds. Doing this practically, we measure a period of 0.64 seconds, agreeing with theory with a deviation of 1.6%. When arranged in series, the inverse of the combined spring constant equals the sum of the inversed spring constants, which predicts a period of 1.25 seconds. Doing this practically, we measure a period of 1.28 seconds, agreeing with theory with a deviation of 2.3%. I have here an oscillating mass on a spring, recording the period for 5 different amounts of mass, and plotting this on a graph. We observe a square root relationship, which is consistent with the theoretical equation. SHM Equations. A system in simple harmonic motion follows a sinusoidal relationship. Sinusoidal meaning that the displacement will follow this hopefully familiar curve. And for the explanation that follows, recall that omega is equal to the displacement over time, and note that if we rearrange this for angle, we get that the angle is omega t. So if we have a pendulum with the displacement beginning at 0, as mentioned, the displacement is going to follow a sinusoidal relationship, where what a sine function does is oscillate between 1 and -1. So our equation for displacement is going to be sine of our angle, which is omega t, where instead of going between 1 and -1, because our pendulum has some amplitude, we want it to go between our amplitude and negative amplitude. To do that, we just multiply our sine function by the amplitude. For a pendulum beginning at the amplitude, the equation is the same except with a cosine. The reason this is because this graph here is a sine function, which because sine of 0 is suitable for beginning at 0. However, if we're starting at our maximum amplitude, we need a function that starts at the amplitude, which is exactly what a cosine does. If you wanted to test this out, put into your calculator sine of 0, and you'll see that that will equal 0, whereas cosine of 0 is going to equal 1. And now for each of these situations, we have velocity and acceleration terms. These equations are given to you on your formula sheet, though for those of you who are calculus-minded, we can differentiate our displacement equations with respect to t, which will give us our velocity equations, and differentiate our velocity equations with respect to t to find our acceleration equations. Don't worry if you don't understand what I just said, calculus is not required for level 2 or 3 physics. And now let's ask the question, what is the maximum displacement, velocity, and acceleration? As mentioned, each of these trigonometric functions just go between 1 and negative 1. So the maximum that these equations can be is 1. And so we see our maximum displacement is 1 times our amplitude, which is just our amplitude, which shouldn't be surprising, as this is literally its definition. For our maximum velocity, we see that the greatest these equations can be is a omega, therefore our maximum velocity must be a omega. For our acceleration, the greatest that these equations can be is a omega squared, and so our maximum acceleration is a omega squared. Let's use this in an example. A pendulum with a 1 second period is released from its amplitude. How long does it take for it to fall to half its amplitude? To find this out, we first need to determine the angular velocity, which is equal to 2 pi f, and because we're given the period and not the frequency, we can substitute in that frequency is 1 over period, put in our 1 second, which gives us 2 pi. Now to relate our time and our displacement, we can write the equation that when our displacement is the amplitude over 2, half the amplitude, that is equal to our equation a cosine omega t, where t is what we're trying to find. Solving this for t, we can first divide out our amplitude, take the inverse cosine of both sides, and then divide both sides by omega and swap them around. Substituting in our omega gives us 0.167 seconds. Let's now view our two situations on graphs. For our displacement beginning at 0, we have the equation y equals a sine omega t. Because it's a sine, it starts from 0, as we'd expect given our initial condition. Our velocity equation is a cosine, meaning that it starts from its maximum amplitude. This makes sense because our maximum velocity is expected when our displacement is 0, meaning when our object is at equilibrium. For example, if we have our pendulum, as it swings, its maximum velocity is going to be reached at equilibrium. Furthermore, its velocity is going to go to 0 when it's at its maximum displacements. Our acceleration equation is proportional to a negative sign, which means it has the same shape as our displacement, except because it's negative, it's flipped upside down. This should make sense, being that one of our conditions for simple harmonic motion is that the acceleration is opposite to the displacement. For the situation where the displacement begins at 0, we essentially have the same relationships, except that we start at the maximum amplitude, so that the graphs over here are exactly the same as the graphs over here if they were to start over here. SHM and circular motion. Until now, we've represented SHM on displacement versus angle graphs. However, we can also represent it as an analog of circular motion, which we call phases. And so we imagine an amplitude vector rotating counterclockwise in a circle. Our equilibrium is represented by this horizontal line here, and the vertical distance from the equilibrium to the tip of the vector is our displacement y, where the angle the vector is tracing is the same angle that we're indicating here. So that if our amplitude vector starts here, that is represented here on this graph. If it then rotates to an angle of 90 degrees, that corresponds to here, where this angle here is 90 degrees. Rotating further, we get to 180 degrees, represented right here, where you might note that our displacement is once more 0. Rotating further around to 270 degrees, we are now located right here, and rotating another 90 degrees gets us back to where we started, and we've performed a full rotation. And now you might recall the equation for centripetal acceleration, as our acceleration is equal to velocity squared over r, where in this case our r is our amplitude. So we can write that the linear acceleration is equal to our linear velocity squared divided by the amplitude. Furthermore, recall that velocity is distance over time, which we can write as the distance for one rotation, which is the circumference, divided by the time for one rotation, which is the period. I have here a phasor circle and a sine graph side by side to show how one relates to the other. Starting at 0, we can represent a full revolution, where on the phasor diagram, the angular displacement is literally the angle, whereas on the sine graph, angular displacement is represented linearly. To describe this mathematically, we define the amplitude A as the maximum displacement, represented as the radius of the circle, where if the phasor has rotated through some angle theta, the linear displacement y is the vertical displacement from equilibrium. This gives us a right-angled triangle, where we can use the SO in SOHCAHTOA to write opposite over hypotenuse is sine of the angle, where the opposite is the linear displacement y, and the hypotenuse is the amplitude A. Rearranging this for y by multiplying both sides by a, we get an equation for linear displacement in terms of the amplitude A and the angular displacement theta. Let's now go through an example. A mass on a spring is lifted 0.150 meters and released. It oscillates with a period of 0.855 seconds. How long does it take to fall 0.200 meters? And so, drawing a phasor diagram, because our spring is lifted before it's released, it is starting from its maximum displacement. Our maximum displacement on our phasor diagram is located either here, or if you wanted to, you could draw it over here, where we know that this distance here is 0.150 meters because it is our amplitude. And so if our mass has fallen 0.2 meters, we know that it must be below this point, and so we can imagine the phasor arrow pointing here, where this distance here is our 0.200 meters. To relate our displacement and our time, we can use this equation here, where we are using the cosine equation and not the sine equation, because we're starting at the maximum amplitude. And now we know the y value, that is our 0.20 meters. We know our amplitude, we're given it up here. We're trying to find our time, but we don't know our omega. To find that, we know that omega is 2 pi f, frequency is 1 over period, so we can make that substitution, put in our number, and find 7.35 radians per second. Knowing this, we can now solve for time. Our first step is to divide both sides by the amplitude, take the inverse cosine of both sides, and then divide both sides by omega. Putting our numbers in gives us 0.260 seconds. Energy of SHM. The energy of a system in SHM is traded between kinetic and potential energy. So if we consider an example where the total energy remains constant, as our kinetic energy goes down, our potential energy goes up, and vice versa, such that at any one time, the sum of these two is going to equal our total energy. In any undriven system, however, meaning that energy isn't being inputted into the system, energy is gradually lost. We call this damping. The key feature of this graph is that although the amplitude is decreasing, the wavelength stays constant. Resonance. Adding energy to an oscillating system is called driving. Every oscillating system has a natural frequency. Inputs of energy at this frequency will constructively interfere with the existing energy of the system, resulting in an increase in amplitude. Inputs of energy above or below this frequency will destructively interfere with the existing energy of the system, so our amplitude will decrease. For example, if you were pushing a swing, if you were to push the swing too late, then some of your push would be wasted and you'd end up pushing air. If you instead pushed the swing too soon, then you'd be pushing against the swing, applying a force in opposition to its velocity, decelerating the swing and removing energy from the system. If you push the swing at just the right frequency, meaning at the natural frequency, then you're always pushing with the motion of the swing and therefore adding energy to the system.